So we'll talk about, I'll give you a brief introduction on randomized algorithms, just to give you a feel of the entire course. There are so many more things that I want to talk about, but I will not be able to cover. So one disclaimer that I want to give before starting is that I didn't have much time to prepare for this course, short course. So it might seem a little bit patchy. So please bear with me. So if something is not understood, I don't have things to cover. We don't have a syllabus, right? So stop me and we can go into the details of anything that you want to discuss more. Okay, so when I teach randomized algorithms, these are the two books that I recommend. Okay, so the randomized algorithms by Motwani and Raghavan. This is the classic book that is used for randomized algorithms. And more recently, it's not recent, but more recently compared to the Motwani Raghavan book, is a book by Midzenmacher and Upfel. And both of these books give you a sort of very nice comprehensive overview of randomized algorithms. Okay, so if you want to learn randomized algorithm, then I would recommend these two books for this. Okay, so let's go over the introduction, the definition of what do we mean by randomized algorithms. Okay, so before we go into randomized, so what is a randomized algorithm? Well, randomized algorithm is an algorithm that has an additional random input bit. Okay, so these are just algorithms which has an extra resource, and this resource is the ability to toss random coins. Okay, so this is one of the ways to look at it. Another way to look at it is randomized algorithms are just algorithms that have an additional input, which are random bits. Okay, so they have the input, the classical input, and some random bits, and your algorithm is allowed to use the input and the random bits to produce an output. By the way, what is an algorithm? How do we define an algorithm? Finite step. Okay, so it's so. Say that again. Must terminate. Otherwise, not an algorithm. Okay. So yeah, so let's not go into the details and the mess involved in termination, non-termination. An algorithm is sort of a step-by-step way of solving a problem. Okay, so that's the meaning of algorithm. And this definition basically works when we try to learn algorithms. Okay, when we try to learn algorithms, when you try to learn randomized algorithms, but this definition somehow fails when we try to understand what an algorithm is not capable, when we can't come up with an algorithm for a certain problem, right? Then the step-by-step way of solving a problem, this definition is not good enough, right? We have to understand who is conducting these steps. Okay, what is the entity that is conducting these steps? What is an individual step? If we don't answer those questions, we'll not be able to answer questions like, look at this problem, there cannot exist an efficient algorithm for this problem, right? So unless we try to understand, get a more better or a more precise definition of an algorithm, we'll not be able to answer those questions. But looking at it from the upper bound side, that means you're trying to solve problems, you're trying to come up with the ways to solve problems, this definition is good enough, okay? And even for this discussion of randomized algorithm, that definition is good. And the definition is a step-by-step way of solving a problem. So what are we talking about? So it's just an algorithm, except that here you have an additional input, and the input are these random bits, and you're allowed to use these random bits in any manner that you want. Okay, so why do we study randomized algorithms? What is so special about randomized algorithms as compared with classical algorithms? Okay, so remember, randomized algorithm is just an algorithm with additional random bits. Okay, so in many cases, randomized algorithms, if you are allowed to use randomness, then it greatly simplifies the deterministic algorithm. Okay, so the first reason to use randomized algorithms is that in many cases it simplifies the classical deterministic algorithm. Do you know of an example, any example where the randomized algorithm actually simplifies? The randomized algorithm for the problem, for the same problem, is much simpler compared to the classical algorithm. median finding, well, you can, well, okay, so I'll give you that, because there is a deterministic way of doing things, and there is also a randomized way of doing things. There are many other examples, right? So for checking whether a number is prime or not, so it was known for a very long time that they're very simple, these very simple randomized algorithms that very quickly check whether a given number is prime or not. And it was not known whether there would be a deterministic algorithm that solves the problem. And it was a big breakthrough when it came out in 2003 that you can have a deterministic algorithm to solve the same problem. And still, and yet, the algorithm that people use to check whether a number is prime is not the deterministic one that came out in 2003, which is a slightly more complex, but they still use the randomized one. Okay, and these are a few examples where randomness actually greatly simplifies. Okay, so it's used as a sort of a simplification. You have a very simple algorithm if you're allowed randomness. Okay, now there are efficient randomized algorithms for certain problems for which no deterministic algorithms are known. Okay, so there are instances where randomness actually helps, really. Okay, so you have efficient randomized algorithms, but you do not know whether efficient deterministic algorithms exist or not. And this is sort of a big open question, okay, in theoretical computer science. The question that people are trying to explore is that, does randomness buy you anything as far as computational efficiency is concerned? So there is a big, like a lot of people actually think, researchers think, that randomness does not help as far as computational efficiency is concerned. And there are some other few people in minority which think that actually randomness helps. Okay, so it's a big open question. Okay, so it's like P versus NP question. Okay, so it's big. People really want to understand whether randomness buys you anything or not. Okay, let's not go into the details of, again, it becomes very messy unless we talk about a few examples. Yeah.
Second point is maybe there are not.
It's an open question. We don't know. If randomness does not help, if it resolves in one way, then we get that no, randomness does not. For any problem for which there is an efficient randomized algorithm, there would also be an efficient deterministic algorithm. But if it does not resolve in that sense, then there would be a problem. There will exist a problem for which there will be an efficient probabilistic algorithm and not a deterministic one, right? So that's why it's unresolved. It's open. We don't know. Okay. So right now there are problems for which efficient randomized algorithms are known, and it is not known whether there can exist an efficient algorithm, a deterministic algorithm. In many other cases, randomness can be used very nicely to break symmetry. Suppose in distributed settings, right? So for example, what could be an example? So maybe Ethernet, right? So you know how communication happens over Ethernet? So there are all these computers connected over the Ethernet wire. How do they try to communicate? Because only one computer can sort of shout out or send bits through the common network, right? So how do they do it? Suppose everybody simultaneously starts talking, then it doesn't work, right? Because everybody is simultaneously trying to talk on the same Ethernet wire, it does not work. So how do you break that symmetry? Using some randomness, right? What they have is like they have a wait time which is randomized. You pick a randomized wait time and then you keep doubling it, and they're a complex protocol. But that is an example where randomness really helps to break the symmetry. There are all these entities which do not talk to each other, and they somehow have to synchronize. Okay, and randomness provides you one way to break the symmetry. Okay, so that's why. So it's in many cases it simplifies. There are instances where you get efficient randomized algorithms, and randomness gives you a very good way of breaking symmetry in a few cases. Okay, so that's why we study randomized algorithms. Okay, so what should you expect to learn in this brief introduction? We're going to cover some very basic techniques just to get warmed up to design algorithms for some very simple problems. Some techniques for analyzing randomized algorithms, and we'll talk about a few things: hash functions, Kargar's algorithm, most likely not Lowa's local lemma. So, but hash functions, Kargar's algorithm, perhaps, no, not perhaps, I will talk about randomized quicksort. Okay, so let's start with hashing. what is the goal of hashing? What is the problem that we're talking about? You have a set of S keys from a large universe. Okay, so the universe is these numbers 0, 1, 2 up till m minus 1. Okay, and you have S keys out of this universe, and they are supposed to be stored in a table which is a very small size. Okay, and the table have entries labeled 0, 1, 2 up till n minus 1. Right, so you have a very large universe. Okay, and you have a small table indexed with 0, 1, n minus 1. Okay, and you have a set S from this universe, and you want to store this. Okay, this one.
Anyone.
And you want to store these elements, these keys in that particular table. Right? So how do you do that? Well, you use a hash function. Where do you want to store this? Okay, so you take a particular element from this set S. Where do you want to store this? Which table entry do you want to store it? Right? That's the question. And one way to do it is to come up with a hash function. Okay, so a hash function is a mapping from the elements in the universe to 0 to n minus 1. Right? So you come up with a hash function or a function h, and then to decide where does this element go, you just compute h of this, and then you decide, okay, so h of this is basically this table entry, so let's say a should go here. Right? So that is how you do it. And the whole idea of hash functions is that there shouldn't be collisions. There shouldn't be many collisions. Okay, so there are ways of resolving collisions, but if suppose all the elements map to the same entry in this table, then you have a problem, right? Because then you're basically saying that you're trying to store it in this table, and all these elements go into the same table entry. So then you have to have a linear chain or something, right? So that's how you resolve collisions. And then the operations will be very costly. Each operations are going to be very costly. Insert is going to be very costly because it's a long chain, right? Delete is going to be costly, or search is going to be costly, right? So the idea of hashing is that you want to come up with the hash function h, so that when you apply h on these elements, they sort of map to different table entries. They spread out. That's the intuitive way of doing things, right? You want a function h that spreads out these elements in the entire table. Okay? Okay, so now, is this clear? If m is larger than n, then any deterministic function h is bad. Right? You don't want collisions. Okay? And you have a very large universe. So if you fix your hash function h, okay, then you can always come up with a set S which will be bad for that hash function. Does this statement make sense? If you fix your hash function, then I'm the person who's trying to fix the hash function. You are the person who are trying to come up with a set. If I fix my hash function, you can always come up with a set, okay, S, so that all the elements are going to map to the same table entry. Okay? So that is what I mean by if m is greater than n, then any deterministic. So I can't fix my hash function. So what is the way to deal with this? The basic idea is that I want to spread these elements along. Okay. So how do you solve that? How do you solve this problem? So one way to do this is I don't commit to the hash function. If I commit to a hash function, you will come up with a bad example. Okay, example that is bad for that hash function that I picked. So what I'm going to do is I'm not going to commit to the hash function. Okay, I will pick a hash function at random. Okay, so that whatever input you can think of, okay, there might be a few hash functions from the hash function family that I'm picking that is bad for that input, but there's going to be many more which is good, which is going to spread out. So now whatever input you fix, since I'm choosing at random from the hash function family, there's a good chance that I'll pick a hash function that spreads out your input into the table. Right? That's the whole concept. Right? So that's how you use randomness in this particular setting. Okay? So main idea, choose h randomly. Don't fix it. Don't fix it deterministically. Choose it randomly. Choose h randomly from a hash function family. Okay. So don't fix a hash function from u to 0 to n minus 1. Consider a set of these functions, a family of these functions, and then pick one at random. Okay? And there's a good chance for whatever input you give me, there's a good chance that I'll pick a hash function that spreads this set nicely, and there are no collisions in this table. Okay? Okay, so let's consider a very basic, very bad, we'll have perhaps have a discussion towards the end, but let's consider a very naive kind of hash function family. Okay, so and the hash function family that we'll consider is all functions from u to 0 to n minus 1. Okay, for all the functions from the universe to 0 to n minus 1. All functions. Okay, that is a set of functions that I'm going to pick, randomly pick my hash function from. Okay, so let's do some exercise. Okay, we're going to come back to this. Why am I saying that this is a bad hash function? Any idea before maybe we can have a short discussion right now. Why is this hash function bad? Hash function family is bad.
How do you resolve the inverse?
When you have to find, search it, how do you search it? Which hash function you use when you are storing it? How will you find that? From where will that value be stored?
Okay, so you're hinting at the right, yeah, so can you formulate a little bit more? The probability of collision we'll do, right, and probability of collision will be small.
Inverse of the.
We don't need to find inverses, right?
If I'm searching for something, when I store, I use a particular hash function. But when I have to search suppose something for that keyword or where I stored, then how do I remember which hash function I use when I store?
But that's the whole concept. When you use hash function, you remember, right? You store the hash.
Then there is only one hash function. But if now when you are saying family, then I have to first select the hash function. So what hash function was used to store?
Okay, so the way randomized hash functions work is that you pick one hash function at random and then you fix it and then you use it. That's the way it is used. You don't, otherwise it doesn't make sense, right? So every time you have to store a number, you pick a hash function, then the whole thing doesn't make sense, right? So you randomly pick a hash function and you fix it and then you use that hash function.
Then it becomes deterministic. Then is as good as deterministic?
No, so it's not deterministic exactly, right? Because I have not committed to that hash function, right? So you gave me the input first. The input distribution was first defined, okay, and then I picked the hash function at random.
For a particular key, fix the hash.
But this is what we say,
For
the
the
hash
hash
function.
function, not for
Huh? For the whole input. Yeah, the hash function is fixed for the whole input. So
The good hash functions will be say that depends upon the input.
Okay,
If
so-
the properties of the input, so then accordingly we decide what hash function should be used.
Okay, so here's the thing, right? So you're right. If you know the input distribution, if you know the input, then you can deterministically pick a very nice hash function for that, right? Suppose you don't know the input a priori. What is the input distribution? Then how would you choose it? How would you pick a good hash function?
Something has been used and
Exactly.
values has been giving good results. That is the hash function that should be used.
No, but you don't know the input, right? If you don't know the input,
The
then
hash function which has been giving good results in different scenarios that can be the option.
but the new scenario could be n plus 1th scenario, right? You don't know.
The probability is always there.
But yeah, so there the problem, it's the input distribution is sort of fixed, but you don't know it, right? So that's the challenge. The input is fixed, distribution is fixed, the input, the keys is fixed, but you just don't know it, right, a priori. And the way to deal with it is, I'm not going to commit to a hash function, I'm going to pick a hash function at random. And with a good chance, I'm going to pick a hash function, even without knowing what the input is, I'm going to pick a hash function that is going to be good for that input. That is right.
That random function give bad results.
Oh, so we're going to bound the probability. We're going to bound the probability.
That in the wrong area, then
Yeah, we're going to bound the probability. We're going to say that that event, the chance of picking a bad hash function is going to be small, whatever the input
And
is.
if we use this capital H, as you were saying, all the functions, all the possible functions, some of these functions can be trivially bad, like something which is like always u a function where I'm saying everything in u maps to 0. And why I would like to consider such a function in capital H?
Yeah, okay, so you can make it as, make this hash function family slightly a bit better, right? But as far as computational probability, will compute the probabilities, even if you take those bad functions, the probability of picking a bad hash function is going to be small, right? So that's what the main idea is. Okay, these are all good questions. Okay, so we are,
The question we were asking was, why is this family H not a good family of?
yeah, so can somebody tell me why this might be a bad?
Probably because I can just randomly this family and then I still can identify a sample which for which the number of conditions is quite because it has not gone any refinement. As he just pointed out that it includes even the trivially bad hash functions, which you can very trivially shed off beforehand itself. So I mean.
No, I'm talking about the family. Why is the family? Why is what could be the problem?
Taken all possible functions from you to
n minus 1, yeah.
n minus 1 as the family H. So even you have even picked the trivially bad hash functions as a part of the family.
But that is fine, right? But that's not a problem. We are going to compute the probabilities.
My point is, I've taken this H which considers all the possible hash functions. What if I examine all these functions and then I identify one sample for which all the hash functions are formed by?
No, but you don't know the input, right? So unless you get the input, how will you even evaluate whether a hash function is good or bad? That's the whole point we are trying to make there, right? You don't know the input, so you will not be able to evaluate whether a given hash function is good for this input or not. You don't know the input, right? What you want to do is you want to randomly pick a hash function and then show that the probability over picking these hash functions, the probability of picking a bad one is going to be small, whatever this unknown input is. Okay, so how large is this universe? How large is this set H?
There will always be collisions.
Huh?
Each hash function will have collisions.
Each hash functions.
Will have collisions because M is greater than N, so there will always be collisions. So
Uh,
we are mapping from bigger set to a smaller set.
Okay, but look, this set S might be small, right? You're right. So if as far as collisions in the function is concerned, yes, because you are mapping a larger set to a smaller set, there will be a collision. But we don't want collisions within S, the input, the set of keys, right? So here we want them to spread out nicely, right? So that is the idea. Okay, how large is this set? N raised to M.
From M to N.
Yeah, so n raised to m.
2 raised to power mn.
2 raised to power mn. How many functions are there from 0, 1 up till m minus 1 to 0, 1 up till n minus 1? N functions? No, I'm talking about how many functions there exist. It's a discrete math question, right? N to the power m, right? Because the first, so the first input could go in any one of these n, and the second one can go in any one of the n. So it is going to n to the m, right? That's large. That's huge, right? Even if you have to convey to somebody that this is the hash function that we are using, is costly, right? So the amount of bits that you will need to express the hash function is going to be m log n, right? And that's very large. So even if you have to, so suppose you use this hash function to save the input in this table, and then you want to give it to a friend and tell that, okay, so this is the hash function that we looked, and you can continue working on this hash table. But then you have to convey this hash function, right? And conveying this hash function is very costly because the hash function family is huge. So we will have to store, just storing this hash function will be m log n, and m could be very large, right? So these are bits, right? So this could be 1,000,000 bits, right? And so in that sense, it's a bad hash function. Okay. So we'll later, perhaps towards the end of this lecture, we'll get a chance to maybe talk about a hash function family that gives similar guarantees but is much smaller than this naive hash function family. Okay, so let's calculate the probabilities, right? So consider t insert operations. Okay, so T insert operations one by one in succession. What is the expected cost of each operation? What do you think? What is going to be the expected cost of each operation? You randomly picked a hash function and then started doing insertions of unknown inputs. Okay, what is the expected cost of the operation? What do you think?
It would be constant. If the either solution is equal to or T, like each the equations in that case will follow a chain.
You're talking about the worst case, right?
Yes.
Yeah, the worst case, all these T entries could go into the same place. But the probability of that event happening might be very small, right? So that's why we are talking about the expected cost of each operation. That's where randomness kicks in, right? That's where will be constant. Expected cost of each of the operations. Suppose we talk about the last operation, right? What is the expected cost of that operation? You have inserted T minus 1 items, and now you are inserting the Tth item. What is the expected cost? How much cost? And the cost is, suppose the Tth item maps to this entry, n by 2. Huh? So? Okay. So you're right. So you just have to formulate it a little bit more. T minus 1 by T. Why would that be the case?
Because T minus 1 have already been inserted.
Uh-huh.
It will n by 2.
N by 2. Okay. Why? So doesn't it look like that it should be a function of T and N?
It will depend upon the probability that as to where all previous T minus 1 insertions happened.
Okay.
But when we sum over all of those, T minus 1 for n.
Okay. Okay. So let me break it down. Okay. So the ideas are there. I just need to be formulated, right? So let's fix a particular table entry, right? Suppose this one. After T insertions, what is the expected number of elements in this table entry that maps to that table entry out of these? T by n. Is that correct? Right? Yes or no? Right. So okay. So we can define the random variable, right? So we can define the random variable xi is equal to 1 if the ith item maps to, let's call this j, okay, to j and 0 otherwise. We can do that, okay? And what is the number of elements here? Is basically x equal to summation xi, right? Right. So each one of them you just take the sum, and that is the number of elements here. And we are asking you what is the expected value of this quantity? What is the expectation of this? So then we are asking you what is expectation of this. So this is going to be expectation of summation I xi. Now, any idea how we can resolve this? How we can simplify this expression? The expectation of a sum. Okay, so everybody is comfortable with this. Okay, great. So linearity of expectation always works, whatever the random variables are. If you have an expectation of a sum of random variables, then that is equal to the sum of expectations. Okay, so then I can take the summation outside. Right? Now what is E of xi for any 1 by n? Right? And since I goes from 1 to t, so this is going to be t by n. Okay? So the expected number of elements in each of the table entries is t by n. Okay? So the expected amount of operation that you need to do for inserting is going to be some 1 plus t by n. Okay? So one for finding out the mapping, and then since these are the number of elements, t by n is the roughly expected number of elements in each table entry, those are t by n, roughly 1 plus t by n. Okay? So expectation of xi was 1 by n. Is that clear to everyone? Because we are picking randomly a hash function, right? We are picking a random hash function. So this element has an equal chance of ending up here, 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 anywhere, right? So that's why it's 1 by n. So the probability that lands in jth entry is going to be 1 by n. Okay, so that leads us to, so this is sort of a very nice application of linearity of expectation, just analyzing hash functions. So you have that the expected number of operations that you need to do is t by n by just by linearity of expectation. Okay, so what is the general statement for linearity of expectation? For any random variables x1, x2 and constant c1, c2, we have that expectation of c1 x1 plus c2 x2 is equal to c1 times expectation of x1 plus c2 times expectation of x2. If I ask you to derive it quickly, if I ask you to derive even a simpler statement, can you do that? How do you derive this expression? That for any random variables x1 and x2, expectation of x1 and x2 is equal to expectation of x1 plus expectation. I will not go into the details, but I just want you.
By invoking the basic definition of expectation
Okay.
and rearranging the terms.
Okay. So okay, I'll give you a small exercise. Try to do that. Okay, we're not going to do it right now, but try to do that. So that will sort of even clear up the definitions of expectations. And there are many students who make when I ask them to do it explicitly, they realize that their notion of expectation was not very clear. Okay, so let's skip that part. Okay, and straight away talk about some very basic probability problems. So here's something called a hat check problem. Okay, n men go to a party and their hats get mixed up. They randomly pick up a hat. What is the expected number of men who get their own hats? Okay, well, let's solve this problem. Simple application of linearity of expectation, or classical application of linearity of expectation. Okay, so now one, sure.
Another person and man go to party and they mix with the booze. So if all n are getting the known hats, then after picking one, no one can get that until the same person.
So you're bringing up a issue with this, or you're trying to understand the problem?
One issue plus one answer is given.
Okay. So you're giving an answer as 1.
One, the answer can be true.
Okay.
Can be true because for putting the first hand, we'll have to take up the another hand.
No, but
If you are talking about hand.
yeah. So if you take your own hat, then no. So I did get the statement.
You said that if we are picking up one hand, then
Let's take a scenario of 3 hats.
Okay.
Let's take a scenario of 3 hats.
Okay. So 3 people, A, B, C, and 3 hats. Okay. So this one belongs to this one belongs to this one belongs to this. Now everything gets mixed up and they randomly pick up a hat. Okay. 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 Well, okay, A can still, so A picks, yeah, A will not get his hat and B will also not get his. Yeah, okay. So there are all these complicated scenarios that are there, right? Yes, I'm not denying that. Yes, it seems, outwardly it seems very complex, right? Because you're right, if A takes this, then A doesn't get his hat, B is now also not going to get his hat, right? So there are these very complex scenarios. But still, figuring out the expected number of people who get their own hats, that is simple by linearity of expectation, right? So that is what, so you're right, so it's complex. So if you think about these combinations, then things get very ugly very quickly, right? But still, I'm asking a very simple question. What is the expected number of people? Okay, 1? Everybody convinced? 1? Linearity of expectation. Okay, so let's define a random variable. What would be a good random variable to define in this setting? Right. So that is a reasonable random variable, right? Right? And what are we interested in? Well, we are interested in this quantity. Okay? And what is the expectation of this quantity? Linearity of expectation. Even though you're right, it looks complex, if you start thinking about the scenarios, it becomes very ugly. But then this is simple. You can calculate the expectation just by linearity of expectation. So linearity of expectation, even though the statement is simple, it gives you some very good, very nice results. Otherwise, which without the linearity of expectation would become very ugly. Yeah.
I think it would be better to give the definition of expected xi just once.
Oh,
EIX.
I see. So,
Just give once, maybe some of them.
so are you comfortable with the definition of linear expectation? Okay, so let me ask you then. So what is the definition? Suppose we talk about a discrete random variable. Okay, so that takes values between 1 and some number n. Okay, so let's talk about the simplest case, discrete case. Okay, so okay, so what is the definition of such a random variable, E of x? Summation over I. So let's take this random variable takes values from 0, 1, 2 up till n minus 1, right? So summation 0 to n minus 1, probability x is equal to I times I. That's it. That's your definition, right? That's the definition. And you can derive the linearity of expectation just from this definition. Okay, so it's not very difficult. Okay, here's another problem, and you might have heard about this particular problem. Very nice problem. Okay, and in many different setups and many different scenarios, analyzing randomized algorithms, this will come up again and again and again. Okay, so this should be one of the things that you actually take back from this short introduction. Okay, so remember just remember this coupon collector. The results that we talk about, just remember this. I'm pretty sure that in the future you will come across coupon collectors at some point. Okay, so the problem is simple. So there are n different type of coupons. Okay, you get a random coupon every day in your newspaper. Okay, so somebody just slides in a coupon and then sends you the newspaper. What is the expected number of days in which you should be able to collect at least one coupon of each type? Okay, so there are n types of coupons. Every day someone randomly picks up coupon and gives it to you. Okay, the question is how many days, what is the expected number of days in which you should be able to collect all types of coupons. Okay, so you understand the problem. So the first day you might get coupon of type 1, coupon number 1. Well, the second day you might also again get coupon number 1. Third day also you get coupon number 1. Okay, So I want to know the expected number of days in which you should be able to collect all of them, all coupons. At least 10, yeah, so we have a clear lower bound, right? That's very simple. You need n days to collect 10 coupons, right? Different n times. I want to know, give me a good upper bound. What is roughly the expected number of days in which you should be able to collect all the coupons? Think about it. Take a guess. If you heard about this before, what would be your guess? Huh? No, 2n might not be good enough. Okay, so yeah, so the answer turns out to be n log n. Okay, and yeah, so remember this, take this message back. So if you have this game and you want to collect coupons of all type, the expected number of days in which you will collect all the coupons is n log n. Okay, and we'll derive it now. Okay, so there are a bunch of definitions, so just follow these definitions. Okay, if you follow these definitions, I think it will come out very clearly. So we define the ith epoch to be the sequence of days starting the day after the I minus 1th new coupon was collected and ending on the day the ith coupon was collected, ith new coupon was collected. Okay, so the scenario could be this, right? So you start on day 1, right? Maybe you collected, on the first day you got a coupon number 5. On the second day you again got coupon number 5, okay, 4, 3, okay, 3, 4. So now you get coupon number 7. Okay, so now you have collected 3 different types of coupons until now. The 4th epoch is starting at this day where you collected the ith new coupon. Okay, and ends at the day where you, okay, so it starts after the I minus 1th new coupon was collected, okay, and ending on the day the ith coupon was collected. Okay, okay, so I think that there is a mistake here. So okay, so let me simplify the example. So let me say this. Right, so now you obtain 3. Okay. Say, so the 3rd epoch will be starting, so will be here, okay, and then you get 5, 4, 3, and so forth. Right. Okay, so now define xi to be a random variable denoting the number of days in the ith epoch. Okay, and note that x1 is going to be equal to 1. Okay. Now what we are interested in is in knowing the expected value of this quantity x1, x2, x3 up till xn. Okay. Okay. Now what do you think is going to be the value of expected value of xi? So it's the days, okay, this xi denotes the number of days you took to go from I minus 1 coupons to I coupons. Okay, you had I minus coupons of type I up till I minus 1, and this is the number of xi denotes the number of days you took to obtain the ith coupon. Okay.
There is a 7 after this, then for the 7 the epoch would be 3.
Okay, so let's see. So this is 7.
This is the first 7. Then
Okay.
The first 3 was the first 3 that you have written.
Mm-hmm.
Is the first time when you discovered the I minus 1 and
That is the 4th epoch. First week should not be there.
No, so okay.
the first epoch should be only 1.
Okay, so the first epoch should be only one, right?
And third is still 4. I mean,
Okay.
yeah.
Okay, so is there a problem with this definition? So, okay, so what I want to say is xi denotes the number of days that you took to go from I minus 1 coupons to, so, okay, so there was an instant at which you received I minus 1 coupons, right? And after that day, your ith epoch started. Because after that day, you took the number of days, you spent a number of days in receiving the ith new coupon.
What is the fifth epoch here? It is 543, right? What
Five-
is the fifth epoch here?
Okay, so the first epoch is here, right? So this is the first, right? Okay, so let's draw out the epochs. Okay, so now what is the second one? Well, this one, right? So this is the first one, this is the second one.
Why is it the first one? One is the first one here, right? Why not just the one?
Yeah, so this is the first epoch, right?
We had a one also.
Oh no, this is, oh no, this is nothing.
Oh, this is nothing?
No, okay.
Oh, okay.
Oh, sorry. Yeah, so we started with 555. So this is the second epoch, right? And then what is the third epoch? Just this, right?
So the fourth
Okay.
one is 543.
Yeah, so the fourth one is seven. Right?
543.
7, right? So, okay, so the definition is third, this is the fourth. Right? Good. 1, 2i. Okay, so now what do you think?
The probability that on some particular day that I'll get an old coupon would be I minus 1 by n.
Okay,
So the probability that I'll get a new coupon would be 1 minus that.
I minus 1, okay.
And that is the probability that I'm getting.
That there will be a
That I'm getting a new one.
Okay.
And then I think use this probability to calculate this expected value.
Okay.
Divided by
number of days.
the number of days.
Bring in
Okay.
number of days.
Okay, so let me show you the expression and perhaps we'll go, so evaluate this in retrospect. Okay, so I'm claiming that the expectation of xi is this number, n divided by n minus I plus 1. Okay, so and we'll use his, okay, so let's talk about this. You're talking about the ith epoch, right? You're talking about the ith epoch. Okay. Now look at the first day in this epoch. What is the probability that you will get a new coupon? No, I'm talking about the ith epoch. Okay. What is the probability that you are going to get a new coupon? 1 minus I minus 1 by n, right? Okay. And again, talk about the next day. What is the probability that you will get a new coupon? Again, the same probability, right? And so on and so on. And when does it terminate? Well, when you get a new coupon. Okay. Does it remind you of some random process? What is the expected number of? If this is the case, right? So, if this is the case that the probability of getting something that will stop the game, that will stop the ith epoch is p, and you want to find what is the expected number of days where you'll
1 by p.
you just invert it, flip it, right? So you remember that game, the coin flipping game. So the probability of, if you have a biased coin, right, which comes to heads with probability p, and the game is you flip the coin until you get heads. Okay, what is the expected number of coin tosses required to get a head? 1 by p. It's the same game. Every day the probability of getting something that will stop the game is p, which is this. So the expected number of times you have to flip the coin, or expected number of days where you will stop the game, or will you get something that you really want, is going to be just 1 by p, right? So the expected value, the expected number of days in going from I minus 1 coupons to I type coupons is going to be this, right? And then what you need to do is, well, take the sum of expectations, right? What is the size of the first epoch, second epoch, third epoch, fourth epoch? Take the expectation of all of those, right? So E of x is just the expectation of all this again, linearity of expectation, E of x1, E of x2, and then you just use this fact, you will get a summation like this, n times 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 up till 1 by n, right? Nothing fancy, I'm just applying this, just using this, just putting this here in numbers. Okay. Are you convinced? Oh, so this is the definition of h of n, right? So h of n, this is the harmonic number, the nth harmonic number. H of n is basically 1 plus 1 by 2 plus 1 by 3. But that's not important, but this is important. This is order n log n. If I ask you to actually prove this, can you do that? Can you show that 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 up till 1 by n is roughly log n?
Yeah.
How do you do that?
Break it into parts. The first part would be like 1, then the club of 2, then the club of 4, and then I can say every club I can bound, and then I'll see roughly log n clubs or clumps that I'm making up to
Okay.
going up to n. So
I didn't-
take the first term
Okay.
as 1 clump, then the next 2 terms as 1 clump. So what I can do is like this: 1 by 3 plus 1 by 4, I can actually bound it by half.
Oh,
Or in other words, I can say 1 and
okay, so, okay,
1
so,
by 3 I can bound by half. Then the next 4 terms I can bound by 1 again. So I make clumps, there will be log n clumps.
1 plus 1 by 2.
Every clump is bounded by 1.
okay, so that, yeah, so that's a good idea actually.
1
So I
by 3
do-
is less than 1 by 2, each of the terms is less than 1 by 2, and then you sum it to the base of 1 plus 1 by 2 plus 1 by 4. Likewise, we go till n to the such power which is equal to the power of half. You take the base as 2, to the power k is equal to 4.
okay, so I'm not sure. It might work, but I have my doubts. Okay, so I'll just give you an idea what I had in mind.
Formula.
Huh?
In the previous session, we used that.
Oh, there was something that is called?
Yeah, bounding by integrals. I mentioned.
Oh, so you know, so you just bounded by an integral. Okay, so you just take an integral of 1 by x, that is log of. I just want to give you a hint of where does this log business come in when you have the expression of this type. It's just an integral of 1 by x. An integral of 1 by x is log x. That is where you get log x. Okay, so that's just.
The application on the same day.
Huh? Yeah, this application is great. Application on the same day. Okay, and that's why you have this. So if you want to collect coupons, very practical problem. And if you analyze basic randomized algorithms, coupon collectors is something that will come again and again and again. Okay. So if you want to collect n types of coupons, you get a coupon a day randomly. Then the number of days in which you will collect all types of coupons is order n log n. Okay. Now computing expectation is good, but in many scenarios you want to go beyond that. It's not good enough. Okay, in many scenarios, just computing what is the expectation of a random variable is not good enough, right? So you have some probability PDF and you calculate the expectation, right? In many scenarios, what you want to do is to analyze how tightly packed is this distribution around the mean. Okay, so you want to figure out what is the deviation from expectation. What is the probability that this random variable takes values that is far away from the expectation? Okay, you want to find out how tight is this random variable around its mean. Maybe the entire probability mass is around that mean, maybe not, right? In many scenarios you would want all the probability mass to be concentrated around the mean. In many different scenarios you might not. You want to figure out this quantity. You want to figure out what is the probability that your random variable takes values that are far from the expectation. Okay, and some of the inequalities that come very handy when you talk about these kinds of things, deviation from expectation, is Markov's inequality and some other inequalities that we are going to talk about. So let me know if this is very simple for you guys. So the Markov's inequality says that if x be a non-negative random variable and a be any number greater than 0, then the probability that x is greater than or equal to a is less than or equal to the expectation of x divided by a. Familiar? Makes sense, right? If I ask you to derive this, can you do that? Markov's inequality is something that you should derive it, just to get a sense of what this statement is saying. Okay, so and we can perhaps derive it just using the definition of expectation, right? So what is the expectation? Suppose again we talk about, suppose we fix the case, okay, very simple case where we have a random variable x that takes values from 0 to n minus 1, right? Let's talk about that particular case. Okay, so 1 through n, okay, so a random variable that takes values from 1 through n. Okay, so now expectation of such a random variable x is equal to summation I right. Okay, so now I have to derive what is the probability that x is greater than or equal to a. Okay, so a is a number between 1 and n. Okay, so how do we change this equality to be able to get that inequality? What modifications do we made in this equality to get that equality? Less than or greater than equal to? So is this greater than equal to, okay, I equal to a to n, probability x equal to I times I? No. No. So is this true? Now I'm just asking about this particular equality, right? So is this true?
We'll have to multiply with that.
Why?
This A may be in the middle somewhere.
So I'm talking about a particular case, right? So we can generalize later on. I'm talking about a random variable that takes values 1, 2, 3, 4 up till n.
As long as this I is non-negative, this
I is non-negative, it's 1 through n, right? So I is non-negative, right? So this is fine. A is a number between 1 and n. Okay, it's either 1 or 2 or 3 or 4, right? So it's fine. So this inequality is fine. Okay, so now what changes do I need to make?
I can be lower bounded by e.
Okay, so is this greater than equal to summation I equal to a to n probability x equal to I times a,
And then just repeat it.
right? And that's it. And then what is this? So this is equal to probability that x is greater than equal to a times a, right? And this gives you that probability that x is greater than equal to a is less than equal to e of x by, right? A very simple observation, just using the definition of expectation. Okay. Okay. So, and a simple corollary of this Markov's inequality is that if x be a non-negative random variable and c greater than equal to 1, then probability that x is greater than equal to c times the expectation is less than equal to 1 times c, 1 by c. And this is exactly what we were looking for, right? Remember, so this is the probability distribution function of this random variable, right? So this is the probability distribution that we are looking for, right? And the expectation was somewhere over here. And what we wanted is, what is the probability that this random variable takes a value that is far away from the expectation? And this is what is exactly what this is saying. This is saying that the probability that this random variable takes a value that is larger than c times the expectation, this probability mass, that is less than equal to 1 times c, right? So it's sort of bounding the tail on the right hand side of the expectation. Okay. Say it again. No, this is any. So I've drawn it like a bell curve, but x is any random variable, doesn't matter. Any non-negative random variable, the inequality holds. Okay, no conditions on the random variable. Markov's inequality hold for any non-negative random variable. So I've drawn it like a bell curve, but don't get misled by that. Okay. Okay, so now let's go back to the heart check problem and see whether we can find more interesting properties in the heart check problem using this Markov's inequality. Okay, so what is the probability that at least 10 people out of n get their own hats? Let's try to analyze that. Okay, the expectation we figured out, that's 1, right? So from Markov, what do we get? We get that the probability that x is greater than or equal to 10 is going to be less than or equal to 0.1. Simple Markov application, you get a very nice property about the hat check problem. If you want to know, if you want to bound the probability of the number of people that get their own hats, Markov's inequality tell you that the probability that at least 10 people get their own hats, that is less than or equal to 0.1. Okay? Now, even though Markov's is good in many different scenarios, it might not give you a very tight bound, very good bound. It might give you a very crude bound. Okay, and here is an example where Markov's inequality gives you a very crude bound. If we want to analyze the probability that everyone get their own hats, then we know that that's equal to 1 by n factorial. Let's see what Markov gives us. Just apply Markov. From Markov, we get that the probability of x greater than or equal to 1 is less than or equal to 1 by n. This is right. The probability is indeed less than 1 by n. But look at it, how far it is from the actual answer. Okay, so the actual answer is 1 by n factorial. But what Markov gives you is only 1 by n. It gives you a bound, but a very crude upper bound. Okay, so when using Markov, you have to realize that it might not be close to the bound might not be very good. Okay, so it might be a very crude bound. Okay. Okay, so now let's talk about another deviation from expectation inequality. This is called the Chebyshev's inequality. Okay, and this says that if let x be a random variable and a be a number greater than 0, then probability of x minus ex mod, the absolute value of this quantity, being greater than or equal to a is less than or equal to the variance of x divided by a square. Okay, so you guys comfortable with variance of a random variable x? Okay, so let me write down the.
Some of them maybe, but
Okay, so let me write down. This is the definition of variance. Variation of a random variable x is just the expectation of x minus ex whole square. Okay. So that is the definition. That is the definition of variance. And what this is saying, is that the probability that x deviates from the expectation by this amount is upper bounded by this quantity. Okay, and this is the nature of the result that we actually were looking for. Okay, so what we were looking for when I initially said we are interested in deviation from expectation is that suppose you are looking at a PDF, right? Probability distribution function, right? So which basically means that x takes this value with this probability, x takes this value with this probability, x takes this value with this probability, right? So this is the probability and this is the number. Okay, so on the y-axis you have the probability, on the x-axis you have the value that the random variable takes. Okay, so we said that, okay, suppose this is the expectation, right? And we are interested in the probability that the random variable is far away from the expectation. So what we are interested in is actually this probability mass. This plus this, right? We are interested in both. Markov's only gives one side. Markov's only tells us what is the probability that x is larger than, say, c times the expectation. What this is saying is that what is the probability that x is away from the expectation by an amount a. Okay, so that is a sense in which, so this is basically a. Right? And you're trying to figure out the probability of the shaded region. And this says that this is less than or equal to the variance of x divided by a squared. Okay, so how much time do I have? We started at 2, right?
15 minutes.
15 minutes. Okay. So since I wanted to talk about randomized quicksort, but I also have the second session, right?
Yeah.
Okay. Can you derive this using just the Markov's inequality? Definition, the definition of variance of x is equal to the expectation of this. Okay, so let me define a random variable y equal to x minus ex whole square, right? Then what is the what do we have this from Markov's inequality? Is less than equal to expected value of y divided by a square. What is the expected value of y? The variance, right? From definition. That's what you get there. Okay. So this expression is equivalent to x minus ex whole square divided greater than equal to a square. So the probability of this is the same as the probability of x minus ex whole square greater than equal to a square. That's how you get it. Simple application of Markov's inequality. Okay, but this would be nice in certain scenarios. Okay, now for certain kinds of random variables, don't worry, I'm not going to go into details. I'll just spend like half a minute on this. Yeah.
What do you get for the head check problem using Chebyshev? The claim is that this gives a tight amount, right? I think.
Well, it gives you a sort of both sides, both ends of the tail. Well,
We're not claiming so far?
no, not that. That is not something I'm claiming. Okay. So in some scenarios it might be useful because it's a simple application of Markov's inequality. So it can't be something that is more powerful than Markov's. Yeah, it's nice in the sense that it gives you both sides of the tail. Okay. So in certain scenarios you get much better bounds compared to Chebyshev's and Markov's, right? So if you know something about the random variable x, Markov's and Chebyshev holds for any random variable. Markov holds for any non-negative random variable, Chebyshev holds for any random variable, right? So we might not have those very good tight bounds. But if you have more information about the random variable that you have, you might be able to get much tighter bounds, okay, or much sharper bounds in some sense. For example, here's a scenario. This is called the classical Chernoff bounds, right? So here is a scenario where you have more information about the random variable, and hence you get very strong bounds in such cases. So the Chernoff bounds, the scenario is the following, right? So if x1, x2, x up till xn be independent 0, 1 random variables, and you're considering the random variable x, which is the summation of these random variables, then you calculate the expectation of this x, okay, and take any delta greater than 0, be a real number, then you know that the probability that x is greater than 1 plus delta times mu, the expectation, that becomes exponentially small, extremely tiny. So in this particular scenario, where you have random variables which are 0, 1 random variables, okay, and you calculate the expectation or the mean of such a random variable, what you get from the Chernoff bounds is that random variable is very tightly concentrated around its mean. Okay, such a random variable is basically a summation of independent 0, 1 random variables that is very tightly concentrated around its mean. So you have more information about the random variable x, and you get bounds which are very, very strong. Okay, so let me not go into details of this because I think we'll not use it. So I can upload the slides somewhere, and the statement of these Chernoff bounds might be very useful when you analyze various scenarios. Okay, so let me not go into details of this. Okay, so you even have a special case of Chernoff bounds where you have the information about how this random variable is constructed. Okay. Okay, so just like the coupon collector problem, there's something called a birthday problem in randomized analysis. And again, in many different scenarios, this birthday problem will come up. Okay, so it will be a good idea to discuss or get the main ideas of this problem known as the birthday problem. Right? Everyone must have heard about this in some form or the other. Okay, so let's look at that. So you uniformly sample q items with replacement from a collection of n items. You want to find the probability that there are two items that are the same. Okay, so let's look at the popular version. So that seems like a boring version of this. There are q people in the room. What is the value of q such that the probability of two people having the same birthday is at least half? That's the popular birthday problem. Each person's birthday is assumed to be a random day in the year. So anyone knows about this? There are q people in the room, and everyone's birthday is a random day in the year. How many people do you need in the room to get a collision? That means with probability at least half, two people will have the same birthday. Any guesses? Well, again, we have a crude upper bound, right? If there are 365 people in the room or 366 people in the room, you will get a collision, right? With okay, 23. So what is the significance of 23? So what he's saying is that if there are 23 people in the room, with probability at least half, two people will have the same birthday. That seems very weird, right? 23 is very small compared to 365. And yet, if all you need is 23 people in the room to get a collision for two people to have the same birthday. That's why this is actually called the birthday paradox. There's nothing paradoxical about it. It's just that it seems weird that all you need is just 23 people in the room for two people to have the same birthday with probability half. Right? There's nothing, well, I won't call it a paradox, it's a birthday problem, but it seems, at the face of it seems a little bit weird. What is the significance of 23? As a function of 365. Where do you get 23? What is significance of 23 with respect to 365? That means, what is the function? Okay, so the significant thing that you realize is 23 is roughly square root of 365, and that is the significance of 23. Okay, so you get square root of the number of days. If you have square root of the number of days in the year, those many people in the room, then with good chance there will be two people with the same birthday. You'll get a hit, you'll get a collision, right? And then we can generalize, right? So there's nothing particularly interesting about 365 and people in the room, right? Now we can talk in terms of the general problem. The general problem is that there are a collection of n items and you pick uniformly at random with replacement. How many items do you need to pick before you get a collision? Okay, so this basically says what you are trying to claim is that if you pick square root n items, then with good chance you will get a collision. You will pick the same item. Okay. Okay. So this might be a little dense, but it's okay. So we are going to take a break after this. So just bear with me. So we will derive this. Why is it square root of n? Okay. We will derive it. Exactly. This is exactly what we're going to do. Okay, so here's how we formulate the problem, right? So let xij be an indicator random variable that is 1 if the ith and the jth person has the same birthday and 0 otherwise. I'm talking in terms of birthdays, but you realize that I'm talking about the about the sampling problem, right? So just assume that there are n days in the year, and you're talking about q people. Okay, so right now assume that we're in a different planet which has n days. Okay. Okay. So first, I want to claim that for any I less than j, E of xij is equal to 1 by n. The expectation of xij is equal to 1 by n. Why is that true? The probability that the ith and the jth person has the same birthday is 1 by n.
Pick one, and you have 1 by n probability for the second one.
For the second one, right? So whatever the first guy's birthday is, the probability that the second guy will have the same birthday is 1 by n, right? So the probability that two people I and j have the same birthday is going to be 1 by n. Okay, it's slightly non-intuitive, but you can work out the probability. Actually, it's not. Yeah.
N by n square is directly intuitive.
Yeah, exactly. N by n square. That's what I meant. Well, sometimes it's easier to think directly in terms of fixing the first guy and picking the second one.
Yeah.
But it's better to break it down and do it by n square. Okay, so the expectation of this random variable exij is 1 by n. Okay, it's an indicator random variable, so the expectation is equal to the probability. Okay, so let x denote the number of distinct pairs of people that have the same birthday. Then claim 2 just says this, x is equal to summation I less than j xij. Is this fine? Fine, right? So the number of distinct pair of people which are same. Okay, so claim 3, I'm claiming that the expectation of this random variable x is this. Linearity of expectation, nothing fancy, right? Just you have E of x here, you take the expectation inside, you know the expectation of ij for every I less than j is 1 by n. So you have all pairs of people.
All ij pairs.
Yeah, all ij pairs, right? So then you have q into q minus 2, q minus 1 by 2, 1 by n. This is the expression that you get. So if q is roughly square root of 2n, then the expectation of x is greater than 1. Okay? Okay? And also, if q is roughly something like this, some constant times square root of 2n, then the expectation of this random variable x is 10. Right? Just working with this expression, right? So I'm just fixing q to be square root of 2n, so you have a q squared factor over here. So if you fix q to be root of 2n, then you get q squared becomes n, that cancels out, and the expectation is some constant. Okay, now let's calculate the variance of this random variable xij. Okay, the variance of this random variable xij, I'm claiming it to be n minus 1 by n squared. Do you see why? Okay, so if you follow the definition of the variance, it will turn out that the variance of x, any random variable x, is expectation of x square minus expectation of x whole square. Right? Now what is the expectation? Let's replace it by ij. What is the expectation of xij whole square from there? One by n, right? And this whole square is going to be n square. That's how you get this. Okay, so claim 5. The variance of x is the sum, okay, of variance of xij. Now this is okay, so let let me not go into detail, but okay, so let me assume that this claim 5 is true. Okay, slightly tricky that you can take the summation of this variance and you get the summation of variance of the right hand side. Okay, but you can do this, right? So the variance of x, it turns out to be the variance of xij. I just want it to be an application of Chebyshev, so let me not go into the detail of unnecessary detail of this. Okay, so the variance of x then is going to be just this expression, right? So the variance of this is going to be variance of x is going to be q times q minus 1 by 2, that is basically all pairs, and then you have n minus 1 by n squared from here. Okay, and that, since you are fixing q to be this particular quantity, you get roughly this. That is equal to 10 times 1 minus 1 by n. So by Chebyshev, now we can apply the Chebyshev inequality. We are interested in knowing what is the probability, okay, that x is less than 1. That means there is no collision. The probability that x is less than 1 is less than equal to the probability that ex minus e of x is greater than equal to 9, because e of x is calculated to be 10, right? So this particular probability by Chebyshev is going to be variance of x, which we calculated to be roughly 10, okay, divided by a squared, which is 81, which is less than 1 by 4. Okay, so the probability that this random variable x, okay, or the number of people the probability that number of people there exist two people who are going to have the same birthday, or you pick the same item, okay, the probability that does not happen is less than 1 by 4 if q is roughly square root of n. Okay, so that means the probability that there will be a collision if q is roughly square root of n will be significant. That means greater than half. That's why you get square root of n there. So this is actually one way of analyzing this, and I followed this complex way of analyzing this because I wanted to show an interesting application of the Chebyshev bound. There are multiple other ways where you can derive the same result. Okay, so don't get bogged down. I think the whole sequence of these claims, you might have lost me a little bit, but there are simpler ways to analyze this. And just remember that when you're talking about this particular problem, you're randomly picking with replacement. Then the number of items that you need to pick before you get a hit, before you pick the same item, is roughly proportional to square root of n. Okay, so that is a take-home message that you should get. This derivation, you can go back and there are simpler ways to do it. Right? I also had a simpler way, but then I think I'll not get time to do that. So it's called the balls and bins problem, and you can actually calculate these probabilities. But I think I'm going to skip that. Okay, so is this a good time to break?
Yeah, I guess we have 3 minutes or so.
Yeah, so I think it's a good time to break.
Okay. So, we have some question and answer.
Yeah, sure.
If there's any questions? Okay. So we'll thank you in the next session.
Okay, sure. Uh-huh. Stochastic algorithm.
You can come in front if you don't mind, since we are breaking anyway after this.
But in randomized search procedure, the answer may be different, little bit different, little vary with some mean, and the number of computational steps may also be different for the same in search procedure, randomized search procedure. And what is the difference between randomized algorithm for randomized search procedure and stochastic search procedure?
Search.
Yeah.
Stochastic and randomized, basically.
Oh, so I can tell you about stochastic and randomized, but search I don't follow. Randomized search. So what do you mean by randomized search?
For example, deterministic algorithm, post deterministic algorithm, or deterministic search procedure means the inputs for the same input.
Now I follow what you're trying to say, right? So for randomized algorithm, right? So you have two inputs, Okay, so whenever you have to describe, it's a good question. Let me. So when you describe a randomized algorithm, right? So the description of a randomized algorithm takes the input x, this is the input, and random bits. This is how you describe the randomized inputs, right? And then you define the computation steps. You are allowed to use the input, you are allowed to use random bits. That's how you use. Okay, so there are various ways people describe a randomized algorithm. So you might not give this as an input, but you may toss some coins or call some random functions to get those random bits. But this is another way. So you predefine your random bits. Okay, on an infinite tape, you write the random bits, and whenever you need it, you read the random tape, and get your random bits, right? And you're right. For a fixed particular input, the computation also depends on R, because this can be interpreted as an extra input, right? So whatever this is, for a fixed input, your computation also depends on R, the random bits. So it might be different. Okay, for a fixed input, you might get different depending on the random bits that you have. You might get different output. That's true. Stochastic, the way I interpret it is that you have some certain kind of distribution of the data itself, and you are trying to analyze with respect to that distribution, right? So it could be a stochastic randomized, where you have a distribution on the data itself and you use some random bits, or stochastic deterministic, that you have some distribution on the data and you have a deterministic algorithm running on that, and you just analyze some properties with respect to the distribution that you have over the data. That is how I interpret stochastic, but there might be other interpretations too.